All right, now it's time to take everything we've learned and actually apply it in a real-world scenario. Because let's be honest, understanding regularization is one thing, but knowing how to use it in a model is what really matters. So let's imagine a situation. You're working on a machine learning project. Maybe it's predicting house prices, customer churn, or fraud detection. Your model seems to be working fine during training. It's hitting high accuracy, low error, everything looks great. But then the moment you test it on new data, the performance completely drops. That's when you know you've got an overfitting problem. And at this point, you have two choices. One, you can ignore it and hope for the best. Good luck with that. Or two, you can do what any good machine learning engineer does and apply regularization to fix it. And here's the best part. It takes just a few steps to do it. Now, for those of you who want to follow along with the code, I've put everything you need in the video description so you can download it and test it out yourself. But for now, let's walk through how this works conceptually. First, when you're dealing with a machine learning problem, you always start by loading and preparing your data. This means getting your data set, cleaning it up, and splitting it into a training set and a test set. Because if you don't have a proper test set, you'll never know if your regularization is actually improving performance. Next, you need to choose which type of regularization to apply. If you have a data set with way too many irrelevant features and you suspect some of them are just adding noise, you're going to use L1 regularization, also known as Lasso. This will literally eliminate useless features, forcing the model to focus only on what matters. But if you're working with a dataset where every feature is important, but some of them are just a little too dominant, then you want L2 regularization, or Ridge. This doesn't remove features, but it smooths them out, making sure no single feature overpowers the others. And then, if you want the best of both worlds, you use Elastic Net, which is a combination of L1 and L2. It removes the worst features, but also balances the ones that stay, giving you a cleaner and more stable model. Once you've chosen which regularization method to use, the next step is to actually train your model with regularization applied. And this is where things get really interesting, because when you compare the results before and after applying regularization, you'll notice something fascinating. At first, your model might actually perform slightly worse on training data. It might drop from 99% accuracy to 90% accuracy. And you might think, wait, why am I making my model worse? But then, when you test it on new data, you see the real magic happen. Your model, which was once overfitting like crazy, now actually performs better in the real world. Instead of failing on unseen data, it makes accurate predictions because it's learned to generalize, and that right there is the entire point of regularization. You are intentionally sacrificing a little bit of training accuracy in order to gain much better performance on real-world data. Now, here's where things get even more interesting. How do you know how much regularization to apply? Because if you apply too little, your model will still overfit. But if you apply too much, your model might become too simple and underfit instead. And that's exactly what we're going to cover next: how to fine-tune regularization using hyperparameter tuning and cross-validation. Because here's the thing, guessing the right value for regularization is a terrible strategy. If you want a model that actually performs well, you need a systematic way to find the best regularization strength. And that's what we're diving into next. Let's set the scene. Imagine you're working as a data scientist for a real estate company, and your job is to build a model that predicts house prices. You've collected tons of data: square footage, number of bedrooms, location, crime rates, school ratings, you name it. So you throw all of this into a linear regression model, hit train, and boom, you get a near perfect fit on your training data. But then when you test it on new properties, your predictions are completely off. Prices are all over the place. The model isn't generalizing at all. What went wrong? Your model overfit the training data. It learned every tiny detail, including random fluctuations and noise, instead of focusing on the real patterns. And this is exactly why regularization is critical in linear regression. Linear regression might seem like a simple algorithm, but it's surprisingly prone to overfitting, especially when you have too many features. The more variables you add, the easier it is for the model to pick up on irrelevant patterns. Your features are highly correlated. If two features contain similar information, the model can become unstable and assign huge coefficients to both. Your data contains noise or outliers. If you have messy data, a standard linear regression model will try to fit every little detail even when it shouldn't. Without regularization, your model's coefficients can explode, meaning some variables will get way too much importance, while others might be completely ignored. So how do we fix this? This is where L1, Lasso, and L2, Ridge regularization come in. Instead of letting the model go crazy and assign huge coefficients to certain variables, we add a penalty to control how large the coefficients can get. L1 regularization, Lasso, in linear regression. If you have too many features, Lasso will eliminate the least important ones, reducing complexity. L2 regularization, Ridge, in linear regression. If you have highly correlated variables, Ridge will balance them out, preventing instability. Elastic net. If you need both feature selection and balance, elastic net is the way to go. By adding regularization, your model stops memorizing noise and starts learning the actual patterns. Let's go back to our real estate model. Imagine we have a data set with 100 different features, things like square footage number of bedrooms distance to the nearest school, crime rate, year built, and 95 other things. Now, some of these matter a lot, like square footage. Others? Not so much. Maybe number of trees in the backyard isn't exactly a key predictor of house prices. A regular linear regression model would try to fit everything, including the useless details. But if we apply L1 regularization, Lasso, it will automatically remove the least important variables, simplifying the model and making it more interpretable. On the other hand, if we apply L2 regularization, Ridge, it won't remove features, but it will make sure the model doesn't rely too heavily on any single variable, preventing one dominant factor from taking over. And if we're not sure which one to use, we can go with elastic net, which gives us the best of both worlds. Regularization is non-negotiable in linear regression, especially when you have lots of variables and you need to remove the unimportant ones. Lasso. Your features are highly correlated and you need to balance them Ridge. You want a blend of both, keeping the best features and smoothing the rest. Elastic net. And now that we've seen why regularization is so critical in linear regression, the next big question is, what happens when we apply it to classification models? Because in logistic regression, regularization works a little differently, but trust me, it's just as important, and that's exactly what we're about to dive into next.